All right. So let's talk about the lab. Okay? Some of y'all, first off, you need to calculate, the only math is to calculate your percent yield. Okay? So on your percent yield, how do you calculate percent yield?
Actual over theoretical.
Actual over theoretical. It's not the subtraction. We're not doing percent error, we're doing percent yield. So your actual, you just weighed, right?
Yeah.
What's your theoretical going to be?
3.
The original mass.
The original mass, whatever it was on your penny.
Oh.
Okay? Not just 3, but whatever your penny was originally. Now, what did your penny look like today?
More
Brown. Not like
More
penny.
brown, right? Not real shiny.
Spots of being red, but it was more brown.
Definitely more brown, not real shiny, lustrous copper like a brand new shiny penny. Okay? What do you think caused it to turn brown? It oxidized, meaning combined with oxygen. Okay? So, what's that going to do to the mass?
Increase it.
But you have less copper, it's all copper oxide.
But you have more oxygen. Wait, what?
Did you lose any copper? No, it's just you're adding oxygen to it, right? So it's going to make the mass greater. So that's the reason why most y'all are going to have over 100% yield. What would happen if it was still a little wet?
Even more. It would weigh more.
Weigh even more, right?
Yeah.
Okay? So that kind of counterbalances some of the spills. Okay? That's your yin to your lab procedure yang. Okay? So it's it just balances out as far as how we get more than 100%. Because technically, what other potential error would cause greater than 100%?
Error?
What else could have caused greater than 100%?
Oh, error.
What were you looking for in yours?
Oh, zinc. Like extra zinc left.
If you didn't get all the zinc out, what's that going to do to the math?
Make it
Make it greater as well. So you had all kinds of opportunities to make it greater. Oh, you guys had a lot of opportunities to make it less too. Based upon y'all's ability to take a hose off or not. Yeah, hand sanitizer? Oh, napkin.
Yeah.
Okay. Now, one other thing I want to kind of talk about in the lab. Oh, before I even do this, you're going to turn in questions 1 through 6. Go ahead and just put them at the end of your lab in your manual. Okay? So you have the handout with questions 1 through 6 for conclusions. Number 7, the pictures, just fill those in and you're going to turn that in addition to the lab. Okay? Remember, there's an 8-minute video, 8 minutes and change video out there where I go through and talk about all the different things and helping you fill in those pictures. All right. One of the questions that got asked of me was the name of this.
It's an Erlenmeyer class.
That's an Erlenmeyer flask. Okay? Now, if I put that onto it,
sidearm.
now it's a sidearm flask or a vacuum filter flask. So the only difference is got the little nozzle on it to be able to suck the air out. Okay? Versus a beaker is always going to be that shape. I mean, I'm expecting you to know those types of things by this point in life. Okay? Now, I will just tell you that if you have one, okay?
It's a round bottom.
That's a round bottom flask.
It's a
They
caramel
make,
apple.
they make the chemistry world go round. Yeah, fat bottom girls make the rock and roll go round. Anyway. But it's also known as a Lawrence flask. That's good. You know that from biology?
No, we wrote it down.
We wrote that down a long time ago. Anyway, because we haven't talked about that one. All right, so those are just names of the glassware. Now, one of the interesting things that happened was when we heated up the pale blue copper 2 hydroxide, we heated up the pretty blue until it turned to that ugly brown, right? But then while it was still hot, we used the hot hands to take it off the fire, and then we filtered it right after that. That was where we did toward the end of day 1. But when we put the CuO solid, and it had NaOH in it, plus other stuff, okay, and this was hot. When it came down in here, we were doing vacuum filtration, okay, to the vacuum. Some of y'all started to boil when you put that in there. Why?
Low pressure.
Low pressure, okay, that's the right answer, but let's explain.
The vapor pressure of the liquid was
You're going well. The vapor pressure of the liquid was?
less than the atmospheric pressure, or was it more?
I think that's the question I'm asking.
The atmospheric pressure inside the flask was the same as the vapor pressure of the liquid.
Okay, so boiling occurs. When the vapor pressure equals atmospheric pressure. Okay? Now, for any given liquid, this is the same liquid here that we went to here, so we didn't change the liquid at all. For any given liquid, what's the only way we change the vapor pressure? Heat it up, change in temperature, right? A change in temperature changes the vapor pressure. You heat it up, speed them up, they evaporate more quickly, you get more vapor, you get greater vapor pressure. So normally, we make something boil by putting it on the stove and making the vapor pressure get higher and higher and higher until it equals that prevailing whatever the 1 atmosphere pressure is around us. Okay? But in this case, the temperature, it was hot, but we didn't increase the temperature. What did we do?
Increase the pressure.
Decrease the atmospheric pressure because we had to a vacuum, we had suction filter, so the pressure inside here was less, so much less that they ended up equaling at the less than boiling temperature, a normal boiling temperature of the solution. Now, did anything else do that? I know they did it happened in first period. It didn't happen to anybody?
Mine and Hampton's.
Okay, I thought I saw at least one. Okay? Now, did it keep boiling for a long time or just at the beginning?
Just at the beginning.
Just at the beginning. Because the high-speed molecules are the ones that evaporate first. The ones that have the most energy are the ones that form the bubble first and escape. So what's going to happen to the average kinetic energy as the fast ones leave? It's going to go down. So the boiling is a cooling process. So the temperature actually, as it boils out, the temperature goes down, especially if we're not adding any more heat back to it. Okay, we had it off the fire, so now we're not adding any more heat. Now what happens if I do the reverse, if I increase the atmospheric pressure?
It stopped boiling.
It would stop boiling. What's that going to do to the boiling point?
Increase it.
Increase it. That's what your car radiator does. Your car radiator has pressure on it on the inside, and so even though the water is above 212 Fahrenheit, above 100 degrees Celsius, it's still not going to boil because it's got the pressure on it. Okay? Now, you have a radiator to cool it as it goes through to get it back down, you know, but if you get a crack in a radiator hose, well, when that comes out, it doesn't come out as water. You start seeing the steam coming out of your engine. I don't know if any of y'all had the unfortunate experience of, seeing, you know, your car break down with a busted radiator hose. But you start seeing steam pouring out of the front of your car. Because you're lowering the pressure, and so the water's so hot, it's immediately flashing into steam as it's able to escape through the crack. Because the pressure is no longer as high because of the crack in the hose. Okay? So these are just practical examples of your vapor pressure and atmospheric pressure. Okay? So that was just kind of an interesting phenomenon that occurred just as we went in there. So we do need to know this. Okay, this is not just on my information, but I do want you to know boiling occurs, vapor pressure equals atmospheric pressure. Normally, we just increase the temperature to increase the vapor pressure to make it equal, but we can also change the pressure and make it boil at any given temperature. All right. Good stuff. Your lab then is going to be due
No.
Friday.
Now.
Ideally, I really wish, I'm very glad we're not in school on Wednesday. But I wanted to have the test on Friday. Yeah, and then just have a whole week to do gas laws before Thanksgiving. And then get most of that done, and then we might even be able to get into some thermo before Christmas, and that would be awesome.
Wait, so
Okay.
next week is the week before Thanksgiving?
That's the stuff.
Next week is the week before Thanksgiving.
That's
We have
crazy.
this week, we have this week and next.
That's so crazy.
I know, and this week's a short week. This week's 2 days off, 2 days, so that kind of really,
What will we be doing on the 2 e-learning days?
that is to be determined.
We're gonna tell what we did today, our activities.
The week of our Thanksgiving break, the Monday